О, работает, отлично. Okay, at the previous lecture we introduced the quantum SU2 group, which is probably the main example of a compact quantum group. So let's recall the definition. We take a non-zero number, non-zero real number q, between -1 and 1, and we define the quantum SU2, or the algebra of continuous functions on the quantum SU2. This is one of the two standard notation, and another standard notation looks like this. So we define this algebra to be the universal unital C-star algebra generated by two elements alpha and gamma, such that the following matrix is unitary. If we write down this condition explicitly, it turns out that this is the universal unital C-star algebra generated by alpha and gamma, such that alpha and gamma satisfy the following commutation relations. Alpha and gamma commute up to q, and the same is true for alpha and gamma star. Gamma is normal. Alpha star alpha plus gamma star gamma is 1, and alpha alpha star plus q squared gamma gamma star is 1. So this combination of equalities is in fact equivalent to the condition that this matrix is unitary. This is an explicit calculation. So this is our algebra. We proved that in the non-quantum case, that is in the case where q equals 1, this is nothing but the algebra of continuous functions on SU2. And actually this was our main motivation for introducing the quantum SU2 group. This is actually this algebra has a canonical comultiplication, delta. It acts to the spatial tensor product of this algebra by itself, and it is determined by the following formula. Actually, this sum has only two summons because we deal with 2 by 2 matrices, and here U is just our universal unitary matrix, which appears in the definition of the quantum SU2. Well, we proved that if we equip this algebra with this multiplication, then what we get is a special case of a compact matrix quantum group. So let's recall that a compact matrix quantum group is a unital C-star algebra equipped with a comultiplication. So a comultiplication is assumed to be co-associative. And together with the matrix, in general it is an n by n matrix with entries in our algebra, such that this matrix and its conjugate matrix are invertible, and such that delta acts on the matrix entries by this formula. So the quantum SU2 is a special case of a compact matrix quantum group. And we also proved at the previous lecture that every compact matrix quantum group is a compact quantum group in the sense of Voronovich. That is, let's write down again these conditions. So these two subspaces of the tensor product of A by itself are dense. They are dense in A tensor A. So these density conditions follow from the definition of compact matrix quantum group, and the quantum SU2 is just a special case of a compact matrix quantum group. Okay, so this is probably one of the main examples, or maybe even the main example of a compact quantum group. It's interesting to compare this object with a purely algebraic object, namely the quantum SL2 group. So let's discuss this relation, the quantum SL2 and the quantum SU2. Well, first of all, let's look at the non-quantum case, at the case of the classical SL2 group. So SL2, we always mean SL2 over the complex numbers. This is the group of all complex 2x2 matrices of determinant 1. Let's look at the following self-map, sigma from SL2 to itself, given by the following formula. It takes every matrix G to G conjugate, transpose, and inverse. So this map is easily seen to be an automorphism of SL2, a group automorphism of SL2. Also, it is involutive in the sense that its square is equal to the identity map. Sigma squared is the identity map. It is smooth, and moreover, its differential at the identity is antilinear over the complex numbers. This is proved by an explicit calculation. And on the other hand, SU2, the special unitary group, is nothing but the set of fixed points for sigma, just by the definition of a unitary matrix. By the way, these conditions together mean precisely that SU2 is a real form of SL2. I'll not give you the definition of a real form in the general case, but basically we have these two conditions. Okay, so let's now look at the algebra of regular functions of SL2. So SL2 is an algebraic subvariety in the space of all 2x2 matrices. So the algebra of regular functions can be identified with the quotient of the algebra of all functions, of all regular functions on the 2x2 matrices, modular the ideal consisting of functions which vanish on SL2. And this ideal, it's a simple exercise to show that this ideal is principal and is generated by determinant -1. Let's write this down in coordinates. So the algebra of regular functions on 2x2 matrices is just the polynomial algebra in 4 variables, A, B, C, and D. So these are just the coordinate functions on 2x2 matrices. And determinant is, the determinant is AD minus DA. So we quotient out the quotient out the ideal generated by this element. Okay, now let's introduce an involution on this algebra. Involution on the algebra of regular functions on SL2 is given by the following formula. If f is a function on SL2, we define f star by the following formula. This is f of sigma of G conjugate, where sigma is this concrete automorphism. It's easily seen that this is indeed an involution, so O of SL2 becomes a star algebra. And in fact, this involution is uniquely determined by its action on the generators. This is a simple exercise. This involution is uniquely determined by the following relations: A star equals D and B star equals minus C. Okay, so the algebra of regular functions on SL2 becomes a star algebra. And it's essential that both SL2 and SU2, both these groups, can be reconstructed from this star algebra. This is also a simple exercise. There is a bijection between SL2 and a set of all unital characters, unital algebra homomorphism from the algebra of regular functions to the complex numbers. Well, actually, every such homomorphism is just the evaluation map at a suitable point of SL2. And on the other hand, SU2 consists of all star characters, of all unital star algebra homomorphisms from our algebra to the complex numbers. So both SL2 and SU2 can be reconstructed from our algebra of regular functions. Okay, now let's look at the algebra of continuous functions on SU2. So it is a commutative C-star algebra. Can we reconstruct this algebra from the algebra of regular functions on SL2? And the answer is yes, we can. Let's consider the restriction map R, which acts from the algebra of regular functions on SL2 to the algebra of continuous functions on SU2. So this is just a restriction map. It takes F to F restricted to SU2. And I claim, this is also a useful exercise, that the algebra of continuous functions on SU2, oh, by the way, let's observe that R is a star homomorphism. So this is a unital star homomorphism, because if G sits in, well, the involution on the algebra of regular functions is given by this formula, and the involution on the algebra of continuous functions is just the complex conjugation. But if G already belongs to SU2, then sigma of G equals G, and this is just the complex conjugation. So R is indeed a star homomorphism. And I claim that the algebra of continuous functions on SU2, together with this homomorphism, is nothing but the C-star envelope. It's the C-star envelope of the algebra of regular functions on SL2. So in summary, we see that if we wish to construct the algebra of continuous functions on SU2 from the algebra of regular functions on SL2, we need two steps. First, we define an involution on this algebra, and then we take the C-star envelope. And this can be used as a tool in the quantum case as well. So let's now turn to the quantum case. First of all, we choose a non-zero complex number Q. A non-zero complex number Q. And we define the algebra of regular functions on the quantum SL2. Well, formally, of course, this algebra is not an algebra of functions, but again, according to the philosophy of non-commutative geometry, we interpret it as an algebra of non-commutative functions on the quantum SL2. This is the unital algebra. It is denoted like this, OQ of SL2, or SL2 of Q. with 4 generators, A, B, C, and D, and the following relations. So the relations look as follows. So to remember them, it's convenient to keep in mind the 2x2 matrix of the following form. So first of all, the elements in each row and in each column commute up to Q. So we have the following relations: AB equals QBA, AC equals QCA, BD equals QDB, and CD equals QDC. Also, the off-diagonal entries commute. B and C commute. A and D don't commute. The commutator of A and D is the following number times BC. And finally, we have one more relation, which is a kind of the quantum determinant. So AD minus QBC equals 1. And this element is usually called the quantum determinant. Okay, so this is our algebra, the algebra of regular functions on the quantum SL2. Of course, let's observe that if Q equals 1, then again, this is nothing but the algebra of regular functions on the SL2 group. Well, indeed, because the first 4 relations mean that the generators commute, so the algebra is commutative. These two elements also commute. And the final relation is that the determinant is 1. So this is nothing but the quotient of the polynomial algebra in 4 variables modulo this ideal. So this is just the algebra of regular functions on SL2. Well, of course, a natural question is where these relations come from. In fact, there are at least 3 possible answers, 3 possible sources for such relations. First, they were introduced by Fadeev and Akhtajan, and their motivation was purely physical. They studied the so-called quantum Liouville model in 1986, and they somehow obtained these relations from some physical considerations. Another source comes from the theory of quantized enveloping algebras, which was founded mostly by Drinfeld and Jimbo, and later developed by many other people. So the main object for Drinfeld was the so-called quantized enveloping algebra, which is a kind of deformation of the enveloping algebra of the Lie algebra little SL2. So he considered, Drinfeld and later Waxman and Soibelman. So Drinfeld did it a little bit unexplicitly, and the explicit construction was performed by Waxman and Soibelman. So they considered finite dimensional representations of the quantized enveloping algebra, looked at their matrix coefficients of these representations, and observed that these matrix elements form an algebra with 4 generators satisfying these commutation relations. And perhaps the most elegant approach to these relations is due to Yuri van Chmanin, who observed that actually these relations don't fall out of the sky, but actually they can be deduced from some very natural requirement. Roughly, the requirement is that quantum groups act on quantum spaces. So if we look at the usual action of SL2 on the 2-dimensional space, just by matrix multiplication, then the dual picture is a co-action of this algebra on the algebra of polynomials into variables. So Malin suggested to replace the polynomial algebra by the so-called quantum plane, which is defined to be the algebra with two generators and the following simple relation. This is a very obvious, straightforward deformation of the polynomial algebra. Malin observed that if we require a certain algebra of 4 generators A, B, C, and D to co-act on this algebra, then we automatically get all these relations, except for the quantum determinant. So this is another explanation where these relations come from. Okay, now let's come back to the quantum SU2. So the following exercise describes a relation between the quantum SL2 and the quantum SU2. So suppose now that Q is a real number, a non-zero real number. Then I claim that there is an involution on the algebra of regular functions on the quantum SL2, uniquely determined by the following formula. A star equals G, and B star equals minus QC. So compare with the classical case. In the classical case, we have this involution, and in the quantum case, we add Q here. By the way, this explains why Q is real. If Q is complex, then this is not an involution. There is no such involution. Part 2. Suppose now that Q is less than or equal to 1. The absolute value of Q is less than or equal to 1. So this is exactly the setting where the quantum SU2 is defined. And I claim that there exists a star homomorphism from the quantum SL2 to the quantum SU2 to the algebra of continuous functions on the quantum SU2, let's denote it by R, uniquely determined by the following property. It takes A to alpha and C to gamma, where alpha and gamma are the canonical generators of the quantum SU2. This is a quantum analog of this map. And finally, part 3, I claim that the quantum SU2, together with this map, is nothing but the sister envelope of the quantum SL2. So this exercise explains a relation between two kinds of quantum groups, the algebraic quantum group SL2 and the compact quantum group SU2. So this one is the sister envelope of this one. Okay, let's now briefly discuss some other examples of compact quantum groups. So let's look at the so-called free compact quantum groups. So the examples we are going to construct are quite different from the quantum SU2 in the sense that they are not related to any kind of deformation. So I have already told you at the previous lecture that in some sense the quantum, these algebras, the quantum SU2 group, can be considered as a deformation of the algebra of continuous functions on SU2. And this informal statement can be made precise if we use some mathematical tools related to sister algebra bundles and strict deformation quantization. So, but informally, these algebras are form a family which continuously depend on this number Q, And if q equals 1, then we get just the algebra of continuous functions. So the free quantum groups are not of this kind. In some sense, there are two kinds of these two kinds of examples correspond to two kinds of non-commutative geometry. So according to lectures by Victor Ginsburg, there are two types of non-commutative geometry. Non-commutative geometry in the small and non-commutative geometry in the large. And what's the difference? Non-commutative geometry in the small studies non-commutative objects, which are, in a sense, deformations of the classical objects. Usually they depend on a parameter or on a set of parameters. And so as a result, non-commutative geometry in the small is a generalization of the classical geometry. It contains the classical geometry as a limit case. By contrast, non-commutative geometry in the large is not a deformation of the classical geometry, and it doesn't contain the classical geometry as a special case. Non-commutative geometry in the large is kind of is a world which is parallel to the commutative world. And the typical objects of this kind of non-commutative geometry is a typical object is a free associative algebra. So it is highly non-commutative, and it is objects of this kind are not deformations of commutative objects. So free compact quantum groups belong precisely to this kind of non-commutative geometry. So let's get some definitions. Suppose that A is a unital star algebra, and U is an n by n matrix with entries in A. And we give the following definition. We say that U is, definition 1, U is biunitary if both U and the complex conjugate matrix U bar are unitary. So let's recall that U bar is obtained by taking the adjoints of the matrix entries of U. Definition 2, we say that U is orthogonal if, first of all, it is invertible. It is self-conjugate in the sense that U bar equals U. And U transpose equals U inverse. And finally, we say that U is a magic unitary. If it satisfies the following three conditions. First of all, each matrix entry is an orthogonal projection. Each Uij is an orthogonal projection. That is a self-adjoint idempotent. Second, the sum of all elements in each column equals 1. And the same is true for rows. For every I, the sum of all elements in the ith row is equal to 1. Uij, of course. A useful exercise is to show that every magic unitary is orthogonal. And it's more or less straightforward that every orthogonal matrix is biunitary. By the way, in the commutative case, every unitary matrix is automatically biunitary. This is also a nice exercise for you. If A is commutative, then every unitary matrix is biunitary. But for non-commutative algebras, this is not the case. And the respective exercise will be included into our exercise sheet, probably with some hints. Okay, so let's now look. Let's now first look at the classical situation, at the non-quantum situation. It turns out that these notions, biunitary, orthogonal, and magic unitary, can be used to give to characterize the algebras of continuous functions on the unitary group, on the orthogonal group, and on the symmetric group in terms of some universal properties. More exactly, I claim that the algebra of continuous functions on the unitary group UN is nothing but the universal commutative C-star algebra generated by the elements Uij, such that the respective matrix is biunitary, or equivalent to just unitary, because the algebra is assumed to be commutative. Similarly, the algebra of continuous functions on the orthogonal group On is nothing but the universal commutative C-star algebra generated by the elements Uij, such that the respective matrix is orthogonal. And finally, the algebra of functions on the symmetric group. Well, I write continuous functions, but of course this algebra is finite dimensional. It consists of all functions. And it is isomorphic to the universal commutative C-star algebra generated by the elements Uij, such that the respective matrix is a magic unitary. The proof is more or less similar to our earlier result, which characterizes the algebra of continuous functions on SU2 in terms of generators and relations. So the proof is more or less similar, and therefore I'll leave it as an exercise for you. The only point is maybe part 3. So initially the symmetric group is not a matrix group, but we can always imagine that this actually is a matrix group. We may embed Sn into On by using suitable permutation matrices. So modulo this inclusion, the proof is very similar to the proof of the respective result about SU2. And let's now just drop the commutativity assumption. So this naturally leads to the following definition, originally given by Wong. I don't remember exactly the year. This is the end of the 1990s. The free unitary quantum group is defined as follows. Again, we have two standard notation. It is defined to be the universal unital C-star algebra generated by the elements Uij, such that the respective matrix is biunitary. Similarly, we define the free orthogonal quantum group to be the universal C-star algebra denoted like this. UN, of course. UN. Or another notation is AO of n. And it is the universal unital C-star algebra generated by the entries of an orthogonal matrix, Uij. And finally, the free permutation group or the free symmetric group is defined to be the universal C-star algebra, AS of n or C plus of Cn, generated by the entries of a magic unitary. So basically we have the same relations as in the classical case, but we no longer require the commutativity. So we get some unital C-star algebras. Why do we call them quantum groups? Formally we have to define a co-multiplication as well. The construction of a co-multiplication is rather easy, because we already have a specific matrix U, which is a part of the definition. And it's natural to assume that this matrix satisfies the definition of a compact matrix quantum group. And this is indeed the case. A more or less straightforward exercise is to show that there is a unique co-multiplication, delta, where A is any of our three algebras. A can be any of them. The formula doesn't depend on the algebra. Such that delta of Uij is the following sum. And moreover, A together with delta and U is a compact matrix quantum group. Well, in fact, the definition is rather straightforward. Let me just explain how we construct such delta. First of all, we construct it formally. So we take our matrix U and we consider the respective matrix over A tensor A. So now to show that this delta indeed determines a star homomorphism, we have to observe that the resulting matrix over this algebra satisfies the same commutation relation. So it is biunitary, for example. If we deal with, if A is this algebra, then the respective matrix over A tensor A must be biunitary. And this is an absolutely straightforward calculation. Okay, so some more information about these quantum groups will be given in our exercise sheet. In particular, a curious property of the quantum symmetric group is that if n is less than or equal to 2, it is commutative and finite dimensional, and in fact isomorphic to the algebra functions on Sn. But if n is greater than or equal to 4, then it is infinite dimensional and non-commutative. Okay, so our next strategic goal will be to construct a quantum analog of the Haar measure for compact quantum groups. But to explain what a Haar measure is, to explain what a quantum Haar measure is, we have to make a short digression into the C-star algebra theory and to define the so-called slice maps. Slice maps on tensor products. Tensor products of C-star algebras. First of all, let's introduce some standard notation. Suppose that H is a Hilbert space. And suppose that X and Y are two elements of H. So we introduce the following operator, which will be denoted like this, X circle Y. This is an operator on H, which acts by the following formula. It takes every element Z in H to the inner product of Z and Y times X. So this is a very simple rank 1 operator. Its range is one-dimensional and is spanned by X. So clearly this is a bounded linear operator. This is a bounded linear operator. And the following simple exercise describes some relations between such operators. For example, if we take a bounded linear operator T, an arbitrary bounded linear operator T on H, then the product of T and the rank 1 operator X circle Y is just the operator Tx circle Y. If we multiply on the right X circle Y T, then what we get is X circle T star Y. More generally, if we multiply T on both sides by suitable rank 1 operators, X, Y, T, and say UV, then the result looks as follows. This is Ty, the inner product of Tu and Y, times the rank 1 operator X circle V. So X and V survive. X is always on the left, V is always on the right, and these three guys give us this number. And finally, part 4, the norm of this operator, X circle Y, is just the product, the norm of X times the norm of Y. Well, this is quite straightforward. Sometimes such operators are denoted as tensor products, as elementary tensors. And this is rather natural because if we try to embed H tensor H into B of H by taking this elementary tensor to the respective rank 1 operator, then this is indeed will be inclusion, or more exactly, to make it well defined, we have to replace H by H complex conjugate. Because this operator is linear in H in X and is anti-linear in Y. But formally, we have to distinguish between elementary tensors and rank 1 operators, so I choose this notation. Okay, so what is a slice map? Well, we have the following theorem. Suppose we have two C-star algebras, A and B. A and B are C-star algebras. And let F be a bounded linear functional on A. I claim that then there exists a bounded linear operator, which will be denoted like this, F tensor 1, which acts from A tensor B to B, uniquely determined by the following formula. It takes every elementary tensor A tensor B to f of A times B. And moreover, the norm of this operator, is exactly the norm of f. Okay, so of course this would be trivial if f were an algebra homomorphism. If f is a star homomorphism, then of course this is true because the spatial tensor product is functorial. This is a functor on the a bifunctor on the category of sister algebras. But f is not assumed to be a star homomorphism. F is just a bounded linear function. So somehow we have to show that it extends to the minimal sister tensor product. Well, the proof I'm going to explain is rather recent. It is due to Pirkovskiy, and it was obtained in 2009. The result itself, by the way, the result itself is quite old. It is due to Pirkovskiy. But the original proof was quite involved and was based on some properties of sister algebra representations. And Pirkovskiy's proof is much more straightforward and simple. So first of all, let's define our map on the algebraic tensor product, which is absolutely trivial. We consider map f tensor 1, which is defined on the algebraic tensor product of A and B. It takes the tensor product to B, and it is uniquely determined by the same formula. It takes A tensor B to f of A tensor B. Clearly, such a map exists and is unique just by the universal property of the algebraic tensor product. So we want to show that this map is bounded for the spatial C-star norm. We want to show that f tensor 1 is bounded with respect to the spatial C-star norm on A tensor B, and moreover that the norm of f tensor 1 is less than or equal to the norm of f. If we prove this statement, then of course we can extend it by continuity to the completion, that is to the spatial tensor product. We still have this inequality, and the opposite estimate is a simple exercise. Just look at elementary tensors. Okay, now let's take our algebra B and embed it into B of H for a suitable H. This is always possible by the second Gelfand-Naimark theorem. Then it follows from the definition of the minimal tensor norm, or the spatial tensor norm, that A tensor B is isometrically embedded into A tensor B of H. This is an isometry. And B is embedded into B of H. And let's now observe that if we construct the slice map here, f tensor 1, then its restriction will be exactly what we are looking for. So this picture enables us to reduce a statement to the algebra B of H. So hence we may assume from the very beginning that B equals B of H. Okay, now let's also observe that our map, so let's denote it by big F, this is F tensor 1, which acts from the algebraic tensor product of A and B to B. So let's observe that F is a B bimodule homomorphism. F is a B bimodule homomorphism. That is F of B u equals B F of u, and similarly on the right. Well, the B bimodule structure on the tensor product is just determined by the action of B on the left and by action of B on the right by itself. And this property is immediate from this formula. So this formula readily implies that F is a B bimodule homomorphism. So let's take an arbitrary element in the algebraic tensor product, A tensor B. So we want to show that the norm of F of u is less than or equal to the norm of little f times the norm of u. So this estimate would imply that big F is bounded and that its norm is less than or equal to the norm of little f. Well, now F of u is an element of B, and B is B of H, the algebra of operators on H. So the norm of F of u can be calculated as follows. This is the following supremum. We take we act by F of u on vector x, take the inner product with y, and let x and y run over the unit ball of H. This is a standard formula which is true for any bounded operator on the Hilbert space. So the norm, oh, I forgot the absolute value. So the norm of any bounded linear operator on the Hilbert space can be calculated by this formula. And to calculate this norm, or more exactly to estimate this norm, we apply the following trick. We take any vector h on the unit sphere and let P denote the following rank 1 projection, H circle H. And let's observe that if we take this number, the number we are going to estimate, and multiply it by P, then this is nothing but the following product, H circle something, F of u, something circle H. And what is something? So we look here. So here we have x, and here we have y. So this follows from formula 3. But now, let's recall that F is a B bimodule homomorphism. So since it's a B bimodule homomorphism, we can now write this as follows. This is F applied to H circle Y times U times X circle H. What can you say about this element in brackets? It's a simple exercise to show that this concrete element, H circle Y times U times X circle H, belongs to the following one-dimensional space. No, not one-dimensional, but the tensor product of A by the one-dimensional space spanned by P. Basically, this is a calculation which is similar to this one. In fact, it's enough to prove this in the case where U is an elementary tensor, and for elementary tensor, this is just a straightforward calculation. So this element belongs to this subspace. So hence you write it in the following form: H tensor Y, U X tensor H. It has the following form: B tensor P for some element B in A. So we can continue our calculation. F applied to this product is just big F applied to B tensor P. And big F is just little f tensor 1. So this is F of B times P. And so let's now take the norm of this operator. So the norm of this operator is just the absolute value of this number. The absolute value of this number, f of y, f of u x y, is the norm of this operator. So it is the norm of this operator, and the norm of this operator is just the absolute value of f of b, little f of b, which is less than or equal to the norm of f times the norm of b. We now replace b by b tensor p. Because the norm of p is 1. And the norm of b tensor p, let's now look here and observe that the norm of this is less than or equal to the norm of u. This operator, the norm of this operator, the norm of this operator are less than or equal to 1. So this is less than or equal to the norm of f times the norm of u. And this is exactly what we wanted to prove. So this is true for every x and every y. And if we now take the supremum over the unit ball, we get that big F of u is less than or equal to the norm of little f times the norm of u. And this shows that big F is indeed bounded, and its norm is bounded, and its norm satisfies this condition. So this completes the proof. So as a corollary, we see that for every bounded linear functional f on A, and for every bounded linear functional g on B, there is a bounded linear functional f tensor g on the C-star, or the spatial C-star tensor product of A and B, uniquely determined by the following property. So it acts at elementary tensors in the following way. Well, indeed, to construct such a functional, we simply compose f and one tensor g. Or equivalently, we can compose g and f tensor 1. In any case, we get a bounded linear functional satisfying this condition. Of course, the natural question is, well, we can perform this construction for star homomorphisms between C-star algebras for the simple reason that the minimal tensor product is a functor. Now we know that we can apply this construction to bounded linear functionals. The natural question is, well, maybe we can extend this to arbitrary bounded linear operators. But the answer is no, and this is a useful exercise. Let H be just little L2. So this is an infinite dimensional separable Hilbert space. And then consider the following map, theta, from the algebra of compact operators to itself, which is uniquely determined by the following formula. If we take the standard of normal basis of little L2, then this number is the inner product of T, Ej, and Ei. So here Ei is an orthonormal basis in L2. Or more exactly, the standard of normal basis in little L2. So roughly, theta is the transpose map. If we represent every operator on H by an infinite matrix, then theta of T is just the transpose matrix. So theta is the transpose map. So the exercise is to prove that theta is bounded. Theta is bounded. But if we take the tensor product of theta by the identity map on K of H, then the resulting map between the algebraic tensor products is unbounded for the C-star, for the spatial C-star tensor norm. So this exercise shows that, in general, our construction is not cannot be extended to arbitrary bounded linear operators. So it works for functionals, it works for star homomorphisms, but in general, it doesn't work for bounded linear operators. Okay, let's now begin discussing the Haar measure. Or more exactly, the Haar state on compact quantum groups. First of all, let me recall, let's discuss the classical situation of compact groups, or more generally, locally compact groups. So suppose G is a locally compact topological group. And mu is a positive Radon measure. On G. In general, it is not necessarily finite. We say that mu is left invariant. Mu is left invariant, or respectively right invariant. If for every Borel set B in G, for every Borel set B in G, and for every element X, we have the following relation: mu of XB equals mu of B. So the left translate of B has the same measure. This is the left invariance, and respectively for the right invariance, we have mu of Bx equals mu of B. If, moreover, mu is not identically 0, if, moreover, mu is non-zero, then such a measure is called a left, or respectively right, Haar measure. Left, respectively right, Haar measure on G. So it is called, it is named after Alfred Haar, a Hungarian mathematician who was a PhD student of Hilbert. And he's famous not only for the Haar measure, but also for the so-called Haar system, which is a special orthogonal family of functions which plays an important role in applied mathematics. Well, natural examples of Haar measure are as follows. We can take either the counting measure on a discrete group, well, if G is discrete, we might define mu of B just the number of elements of B, and this is a well-defined Radon measure. It is indeed a Radon measure because the group is discrete, and it is clearly left and right invariant, so it is a Haar measure. And another classical example is the Lebesgue measure on Rm or on the n-dimensional torus. And in fact, there are many other natural examples which will be discussed in the course Harmonic Analysis and Banach Algebras planned for the next academic year. And we have the following classical result. We have the following classical result due to Haar, von Neumann, and Weil. The theorem states that if G is a locally compact group, then there exists a left Haar measure and a right Haar measure on G. In general, they are not the same. But if you take two left Haar measures, then they are essentially the same in the sense that the only difference is a constant factor. So if we have two left Haar measures, if mu and nu are left Haar measures, then there exists a positive constant c such that nu equals c mu. So in some sense, a Haar measure is essentially unique. And we have a similar result for right Haar measures. And finally, if we assume that G is compact, if G is compact, then left and right invariants are equivalent. Then left Haar measure is a right Haar measure. Left Haar measure is right invariant, and the other way around. And right Haar measure is left invariant. This result was proved in the 1930s. First, Haar proved part 1, the existence of the Haar measure, under the assumption that G is second countable. Then von Neumann proved all these results assuming that G is compact, and the general case is due to André Weil. So what we are going to do is to prove a similar result for compact quantum groups. Of course, the proof will be given at the next lecture, but now, to finish today's lecture, let's just try to understand what is a reasonable quantum analog of the Haar measure. So we use the standard strategy. We take the definition of a Haar measure, and we try to write it in dual terms, in terms of the algebra of continuous functions on our compact group. So we assume that G is a compact group. Suppose that mu is Radon measure, a positive Radon measure. On G. And we define a linear functional on C of G to be the integration with respect to mu. So let's try to interpret the left invariance of mu in terms of a suitable property of H. So we do the following. For every point x and G, we consider the following measure, Lx of mu, the left translate of mu. It is defined as follows. So L mu of B is mu applied to x inverse B. So clearly mu is left invariant if and only if Lx mu equals mu for Lx. So we conclude that mu is left invariant if and only if for every continuous function f on G, the integral of f with respect to mu equals the integral with respect to Lx mu for every x. So these measures are the same if only the respective integral functionals are the same. Well, so this is h of f. This is h of f. And what is this? Well, it's a simple exercise that this is the integral of f of xy d mu of y. This is a little exercise in measure and measure theory. And what is f of xy is just the our co-multiplication delta of f evaluated at x comma y. So this integral is nothing but h composed with delta, sorry, h applied to delta f. Not h. We apply h by the second variable, so this is the slice functional. The slice map H tensor 1 applied to delta f and then evaluated at x. So we come to the following equality. This one is equal to this one. To make this formula even more compact, we introduce some more notation. If A is a unital algebra, let's denote by eta the homomorphism from the complex numbers to A, given by the following simple formula. It takes the identity of the complex numbers to the identity of A.
Why H tensor 1 but not vice versa?
We integrate, oh, of course, thank you very much. We integrate with respect to mu, to the second variable, and yes, you're right. Thank you. 1 tensor H, thank you. Okay, so now this formula reads as follows. Hence, we deduce that mu is left invariant if and only if H equals eta H equals 1 tensor F, 1 tensor H delta. So this equality can be written in the following way. And similarly, we can show that mu is right invariant if and only if eta H equals H tensor 1 composed with delta. And using this as a motivation, we can define left invariant functionals and right invariant functionals on an arbitrary compact quantum group. So our main goal for the next lecture will be to show that for every compact quantum group, there exists a unique state, H, satisfying both these conditions. And this state is naturally called the Haar state on our compact quantum group. Okay, thank you. That's all for today.